Let's start with a really fundamental question, one that sits at the heart of everything from physics to finance. What does randomness actually look like? For a long time, we thought we had the answer, but it turns out we might have been looking at it all wrong.
You know, for decades, our most powerful models have all been built on this one simple idea, that random events, all the noise and unpredictability in a system, follow a nice, neat, symmetrical bell curve. But what happens when the real world is, well, a lot messier than that?
And that gets us right to the heart of the problem. That elegant theory, the one we called the Gaussian distribution, or bell curve, well, it often just plain fails to capture what's really going on in complex systems, like the economy, or even in some physical sciences.
And here's that disconnect, laid out plain and simple. On one side, you've got the ideal model. It's clean, predictable, perfectly symmetrical. And on the other side, that's reality. It's a world full of lopsided results, sudden shocks, and huge, extreme events that our so-called normal models basically write off as impossible. And believe me, that mismatch has some very real, very big consequences.
Okay, so the first major issue is something called skewness. Just think about it for a second. A stock market crash doesn't look anything like a gentle market rise, right? The outcomes are totally asymmetric. You might get lots of small gains on one side, but then rare catastrophic drops on the other. A perfect bell curve just can't handle that kind of lopsidedness.
And the second problem? It's what we call heavy tails. See, in a normal bell curve, those really extreme events are supposed to be astronomically rare. But in the real world, things like market crashes or massive insurance claims, they happen way more often than those models would ever predict. It's like the tails of the real-world data are heavier or fatter than the bell curve allows for.
Now, for years, researchers have been trying to fix this, but they always struggled to capture the full picture, especially that pesky skewness. But what if, instead of trying to fit reality to our model, we could just reshape the model itself? This quote from a really recent paper points to a totally new approach that might have finally cracked the code.
So this brings us to a really cool breakthrough. Imagine this. Instead of trying to find some off-the-rack model that kinda sorta fits our data, what if we could custom tailor our model of randomness to be a perfect match? And that solution comes from these three researchers, Robert Richardson, Dennis Tolley, and Kenneth Kuttler. In their brand new paper, they lay out a completely fresh way to think about and to model these random processes.
They call it the non-Gaussian translation process. Now that sounds pretty technical, I know, but at its heart, it's a really powerful and clever idea. It starts with your basic standard randomness, that bell curve white noise, and then it applies this brilliant mathematical transformation that reshapes it, allowing it to perfectly capture all the skewness and the heavy tails of whatever data you're looking at.
So how in the world does this actually work, right? How do you take that simple bell curve randomness and just morph it into something that perfectly mirrors, say, the messy reality of the financial markets? Well, the process is actually surprisingly elegant. The paper lays it out like a simple four-step recipe. First, you start with your basic ingredient, that standard bell curve noise. Then, you decide exactly what shape you need to match. The real magic happens in step 3, where you apply their special translation formula. And what's the result? A custom-built, random process that fits your real-world data like a glove. The secret sauce here is this idea of matching percentiles. It's brilliant. Imagine you take the 5th percentile point from the simple bell curve. The formula then finds the matching 5th percentile point on your skewed, complex target shape and maps it. And it does this for every single point, the 50th percentile, the 99th, all of them. So it's literally stretching and squeezing the simple bell curve until it becomes a perfect clone of your messy, real-world data. Okay, this all sounds amazing in theory, but you've got to ask the critical question, right? Does it actually hold up in practice? Can it really handle those weird, challenging shapes that we see out there in the wild? Well, the authors put it through some seriously tough simulations to find out. So in the paper, they tested it against some really difficult cases. We're talking distributions with super heavy tails and others with really strong lopsided asymmetry. The goal was to see if their new process could nail these tough targets. And here are the results, straight from the paper. That blue shaded area, that's the complex, real-world shape they were trying to hit.
Now notice that dashed black line? That's the classic bell curve model. And yeah, it's a terrible fit. It's not even close. But now look at the red and orange lines. That's the new method. They are a perfect overlay, capturing both those heavy tails on the left and that super sharp skewness on the right. It's just dead on.
The conclusion from these tests is just undeniable. This new process isn't some minor tweak, it's a precision tool that can reliably create random behavior that follows any structure you tell it to. And get this, even the simplified version they made, which is way faster to compute, still does an incredible job.
So this is way more than just a cool academic exercise. This breakthrough has some really profound implications for literally anyone who uses models to understand and predict what's going to happen in our complex world. Think about it. We can now build far more accurate models for financial risk, maybe finally getting a better handle on what causes market crashes. We can improve economic forecasts. We can better model the lopsided nature of insurance claims. We can even analyze natural events that don't follow the old rules. Basically, any system out there that doesn't fit into that neat normal box is now fair game for much, much better modeling.
And really, the authors say it best themselves. The real game changer is being able to explicitly control for that skewness, that lopsidedness, right inside the random noise of the model. It's just a much more complete and realistic toolkit for making sense of the world around us.
So we started by just questioning the shape of randomness, and we've ended up with a tool that lets us define it ourselves, which leaves us with a pretty fascinating thought to end on. Now that we are no longer chained to the bell curve, what other hidden dynamics, what other complex systems are we finally going to be able to understand?